Okay, section 4.1, defining the atom. One of the biggest problems in chemistry is how do you study something you can't see? If it's so small you can't see it, it makes it difficult to know what's going on. But scientists use some of the same techniques you use here in a month or so. When it gets close to Christmas and you see a wrapped present, you can try and make observations about what's inside even without opening it. The first key question here in this chapter is the concept of the atom, changing from the time of Democritus in ancient Greece to the time of John Dalton. An atom, of course, is the smallest particle of an element that still obtains or maintains its identity. Early Greek philosophers and scientists did not observe individual atoms, but they still proposed ideas about what they were made of. The Greek philosopher Democritus, about in the same time period as Aristotle, Democritus was one of the first suggest the existence of atoms. He used the word atomos, which in Greek means indivisible, to describe these tiny indivisible particles. And that's where the word atom comes from. Democritus used the word atomos because he thought that atoms were indivisible and indestructible. So later scientific theory does agree with Democritus' ideas. He did not explain chemical behavior, and he did not have experimental evidence because it was just a theory. It was just Greek thinkers who were thinking about different ideas. The really truly modern ideas about the atom come from John Dalton, an English chemist and school teacher, and Dalton's atomic theory is extremely important. Dalton used experimental methods and data, and he was able to transform Democritus's ideas of atoms being indivisible into a viable scientific theory. One of the main things that Dalton studied was the ratios in which elements combine in different chemical reactions. And that led to his work, which today we call Dalton's atomic theory. Here are the different parts of Dalton's atomic theory. The first thing he said was that all elements are composed of tiny indivisible particles called atoms, and Dalton referred back to Democritus using the word atomos to mean indivisible. So all atoms of element A are the same. The second part of Dalton's atomic theory says atoms of the same element are identical. So all atoms of element A are the same. And then he said that all atoms of another element, say element B, are different from A. So atoms of B are all the same, atoms of A are all the same, but A is different from B. The third part of Dalton's atomic theory says atoms of different elements can physically mix together, or they can chemically combine in whole number ratios to form compounds. So say, for example, these were atoms of oxygen, and the littler blue ones were atoms of hydrogen. They could mix together, or they could combine in a chemical reaction. If the atoms combined together, it would always be in the same whole number ratio. So, for example, water, H2O, is always 2 hydrogens for every 1 oxygen. And then the next part of Dalton's atomic theory says chemical reactions occur when atoms are separated from each other, joined, or rearranged in different combinations. So they're joined, separated, and rearranged. Then the last part is atoms of one element are never changed into atoms of another element. They always stay the same. We can make new compounds, but the atoms that we have are simply just rearranged in different combinations. So how was John Dalton able to study atoms even though we couldn't see them? He studied the ratios in which elements combine, and observe that when atoms mix, they maintain their own identity unless we have a chemical reaction, and then we get a new substance. So John Dalton really gets the credit because while Democritus had the right idea, it was not a scientific theory and did not have experimental evidence. Dalton was able to take that evidence and then present it as a theory that not only had facts but also explained behavior of elements. This last section is, how do we know what individual atoms look like and how big are they? Liquid mercury that we see here in this picture illustrates Dalton's concept of the atom. Every drop, no matter how big or how small, has the same properties. Even if you could make this very small drop smaller and smaller and smaller, I would still have an atom and it would have the same properties as the rest of the mercury. Copper would do the same thing. If I had a copper coin and grind it into fine dust, each speck still has the same properties of copper. Still make it smaller and smaller and smaller until we finally have just one atom that has the same chemical properties of all copper. Atoms, as you know, are very, very small. A pure copper coin, like a pure copper penny, has 2.4 times 10 to the 22nd atoms. Now that's a lot of. To put that in perspective, we have about 7 billion people on Earth. Well, 7 billion is 7 times 10 to the 9th. So 10 to the 22nd is a whole lot more. If you lined up a 100 million copper atoms, they'd only produce a line 1 centimeter long. Very small atoms are. Well, even though they are very small, we can observe individual atoms with very sensitive scientific equipment such as a scanning electron microscope, also called an SEM. A scanning electron microscope focuses a beam of electrons onto the sample you're trying to look at, and they give us much more magnification than a traditional light microscope that you are familiar with in biology. Not only can electron microscopes allow us to see individual atoms, they can actually allow us to manipulate atoms into specific patterns. This holds some promise in some future technology to make atomic size electronic devices like circuits and computer chips. Imagine how much smaller our electronic devices would be if we had atomic size computer chips. Here's an example of a research project where scientists actually took individual atoms and made them into a car. These pink here items looks like are the wheels of the car, and actually was moved across the surface. This nanoscale, as it's termed, technology holds a lot of promise in medicine, communications, and a lot of other areas as well.